So here you see the graphical user interface of Geodik 2021. The design of the button has changed to a new look, but they are all still available and they are in the same position. One of the first things to do after starting Geodik is to choose a suitable project folder. You can do that in the File drop-down menu, or you can make a right click on the folder path here on the left. I find this more convenient. You can not only choose a project folder, but also open it and see its path. So that is kind of a quick access to your structure and results. Okay, so click on Select Project Folder, make a new folder or choose an existing one, and click on Select Folder. So now let's start to make our first fiber structure. I will guide you through the structure creation, and I will make small breaks in between so that you can follow me on your own computer. To generate a structure, we use the module FiberGeo. You can find that under the model section here. So click on FiberGeo, and then you have different options. You can either create a fiber structure, you can pile fibers, that means that the fibers fall into your domain from the top. You can distribute an already existing fiber structure, or the fibers in an already existing fiber structure. You can add binder to your fibers, and you can also choose between different predefines. The most interesting one for you might be the LamiGeo, in which you can create a stack of several layers of unidirectional fibers, so that you get like a laminate consisting of layers of an on-chrome fabric. But we will go to the Create, and then we click on Edit. Okay, so now we are in the Create options of the Edit menu. And here you can see that first of all we can define the size of our domain. The default value is 200 by 200 by 200 voxels. We are going to change that to 140 by 140 by 140 voxels, and we change the voxel length to 1 micrometer. That then leads to a domain size of 140 by 140 by 140 micrometers. We do that because I want a fast fiber generation for this workshop, so that you can also do it on your computer without waiting too long. Then we have to define the overlap. So you can allow fiber overlap. That, for example, makes sense if you have, for example, polymer fibers that are made in a molten state and they can overlap. But we are going to make a carbon fiber reinforced polymer, and in this case fibers do not overlap. So we click on Without Fiber Overlap and go to Edit. There are now different stopping criterion. So how long does Geodik try to remove all the overlap? You can give a number of iterations, a number of iterations during which the solid volume percentage remains unchanged, and then Geodik stops. And you can also give an overlap. And of course we would like to have 0%, but sometimes it takes quite long to remove the last maybe 0.05% of overlap. And we do not want to wait for that now, so we do not choose 0 but 0.05, just to save us some runtime. And then you have the possibility to choose what Geodik does to remove the overlap. So you can, for example, allow object shifts, we will do that. You can allow object rotations, and you can allow fiber deformations. And for this first example, we want a fiber structure with perfectly straight fibers. So we will not allow object rotations, and we will not allow fiber deformations. If you have that, click on OK. So now we defined the overlap. And then we have to look at the stopping criterion. When does FiberGeo finish the fiber creation? You can, for example, generate a fixed number of objects, maybe like 100, but that's of course not enough for our structure. Then you can define a solid volume percentage you want to reach, a grammage, a given density, or a weight percentage, also a maximum runtime. We will stick to the solid volume percentage, and we will choose 35%. One thing we also have to look at is whether the structure is going to be periodic or not. We are going to make endless fibers, and endless fibers cannot be generated as periodic structures. I will explain to you what periodic means later on, and then you will understand why we cannot make a periodic structure out of endless fibers. So just deactivate periodic for now. Okay, and then now we go on to the fiber options. Under fiber options, you can define which kind of fibers you want to have. And there's quite a large variety of fibers. You can choose them here under fiber type. You can have short fibers, you can have infinite fibers, curved fibers, and also bundles. And as I said before, we want to make infinite fibers for now, so we choose infinite circular. And we click on add. And we remove the short circular fibers. And here now, the first thing you can set is the diameter. We set the diameter to 7 microns. Could of course also not give only one diameter, but a diameter distribution like uniform distribution in an interval, Gaussian distribution, probability distribution, and also log-normal distribution. But as I already said, we are going to go with a constant value of 7 microns. So click OK. And then we have a look at orientations. There's a variety of orientations. The default is isotropic, but of course we are not going to take that because we want a highly oriented composite. So we click on Edit. And now there you can choose. And what I find most convenient for a composite with all fibers oriented in X direction is to go to in XY plane and then choose 0 degrees. Again, you can also use a distribution. They are the same distributions available as for the diameter. Okay, so take 0 degrees and click on OK. You can also save your fibers by clicking on Save here, so that you can use the defined fiber type for another structure you want to generate later on. Now we go to fiber overlap. Under fiber overlap, you can define overlap rules. That is especially important if you have more than one fiber type, and then you can define, for example, that if fiber type 1 and fiber type 2 overlaps, the overlap is going to be fiber type 1 or fiber type 2. We have only one fiber type, so we do not change anything here. And then we also look at the result options. There you can choose whether you want to save intermediate results. We do not want to do that, so we leave it as it is. So then click on OK. And after that, we click Generate. You can see that in this simple case, the generation is really quick. It's already done, and here you can now see this result viewer. The result viewer gives you some information of the generated structure. For example, you can see that the orientation tensor is 1, 0, 0. That means that all fibers are oriented in X direction. And you can see which overlap you wanted to have or you allowed, and that was 0.05. And you can see that Geodict achieved an overlap of even 0.025, so it's even better than we defined. So now we close the result viewer and have a look at the structure. First of all, we are going to turn the structure to get a better look. So you do a right click and zoom in and out, and then with a left click you can turn it. You can move it by pressing on your mouse wheel. So look at it from all sides. And then it can also be interesting to look at the 2D view. So click on 2D here at the top. And then you can slice through the structure by turning your mouse wheel. You do not see any change, but look at the slice controller up here. You will see that it moves. The fact that you do not see any change to the fibers means that the fibers are really perfectly straight in X direction. Okay, so you can slide through it and then go back to the 3D view. You can up here have a look at the percentages of the different components. So we see ID 0, that's polyamide 6, has 65%. And we see ID 1, which are the fibers, with almost 35%. So that's what we defined in Geodict before. But when we look at the structure now, we see that the fibers are not resolved that good. They are a little bit edgy and coarse. So we will now generate the structure again, but with a better resolution. And to do that, we go back to FiberGeo and click on Edit. And to get a better resolution, we want to change the voxel length. We want to reduce it, in fact. So we go to 0.5 as a voxel length. But now, of course, the size of our structure is decreased to 70 microns per edge, and that is too small. We want to have a larger section or the same size of a section out of our material, so we have to double the number of voxels per edge and go to 280 per edge. Everything else remains the same, but you should give your structure a new name. For example, FiberGeo 280. And maybe also add a 0 so that you know that the fibers are oriented in 0 degrees. Otherwise, you would overwrite your previously generated structure. But of course, Geodict would ask you if you want to do that when you hit generate. Okay, so click on OK, and then hit generate. Okay, now here you can see the progress chart. That is the decrease of the overlap while Geodict is removing the overlap. And here, when you click on this arrow, you get also a report, and there down here you can read the current overlap that is still left, and that gives you an indication of how long Geodict will still take, as well as the progress bars here. If you would click on stop now, Geodict would stop at the overlap that it currently has and generate a structure. If you click on cancel, Geodict just cancels the structure generation and no structure is generated. So if you want finish at a certain overlap that you can read there, just click on stop. Okay, so now the structure is generated, and you can again see the result viewer. We close it and we look at the structure, and now you can see that the fibers are way better resolved. They are nicely round and a lot less edgy. The next step is to calculate the stiffness of this composite, because that's a basic information you always need when you want to compare different materials. So that's what we are going to do now. Stiffness calculation is done in ElastoDict, so we go to Predict and click on ElastoDict. In ElastoDict you can choose between different solvers. There's the FEMath AF, which defines mechanical properties by an analytic approach. We are not going to use that. Then there is the solver for large deformations, FEMath LD, and there is the solver to predict effective stiffnesses, FEMath Vox, and we are going to use the FEMath Vox. Of course, we have to make some configurations, and we click on Edit. First, we want to choose the constituent materials. When you are using the Structural Materials edition of Geodict, you already have polyamide as material ID 1. If you use the standard Geodict edition or another Geodict edition like the Digital Rock Physics edition maybe, then there might be another material, the default material for material ID 1, for example air. So those of you who do not already have polyamide 6 here, click on it and then choose polyamide 6 from the material database, and then click OK. And then we have to choose material ID 1, which is the fiber type, and there we go with carbon fibers. So click on carbon fibers and then click OK. So here you see we have now two material types. We have their stiffnesses here, which is in this kind of simulation the most important input. In the second tab, we are going to find the load case. What we want to do is we want to simulate the stiffness tensor. If you want to simulate stiffness only in one direction, please use stiffness in X, Y, or Z direction, and do not just only activate one of those, because this will give you the more accurate result. But we want the full stiffness tensor. As load type we take strain, and as strain increment we take 0.005%. That's a really low strain, but that's also what a tensile testing machine does to measure the Young's modulus. In a tensile testing machine, the Young's modulus is measured at very, very low strains, so that you definitely will not have any plasticity. Then we also have to define the boundary conditions. And here we will assume periodic boundary conditions. I said that we cannot generate a periodic structure from endless fibers, but you saw that our fibers are perfectly straight, and in this case we can, although the structure was not generated periodically, still do a periodic simulation. So choose periodic for boundary condition for tensile loads and also for shear loads. Under the solver tab, you configure the solver. For example, you define a stopping criterion. We use tolerance as a stopping criterion, and because we do not want a very long simulation in this workshop, we increase the tolerance to 0.001. As a solver method, in this case you take conjugate gradient. That's the fastest solver, and that works perfectly for the prediction of the stiffness tensor. Parallelization, take as many cores as your computer has. On my laptop it's 8 processors, so I go with 8. Then go to output. As output, in this case, we just need the von Mises stresses and strains to have something to look at later on. We do not need to worry about post-processing in this case. The only thing that's left is to change the name to something meaningful, and I will change it to 280 and 0, so that we know that this simulation belongs to the structure we made before. Then click on OK. And then you can hit run. Okay, you can again open and close the report with this arrow, and here you will again get some simulation on how far ElastoDict progresses. At the moment, ElastoDict is still initializing and preparing. Okay, and now the simulation starts. There it tells you the size of the geometry. We will also get a graph for convergence. Okay, now the first load case starts. So it says load case 1. All that might go faster on your computer or also take longer depending on your hardware. I'm doing that now on my laptop computer with 8 cores and 32 gigabytes of RAM. Of course, if you have a bigger machine, that might go a lot quicker, and if you have a smaller laptop, then it might take longer. So here you now see the error of the first iteration. And remember, we defined a tolerance of 0.001. So after those first 2 iterations, the first load case is already done. Then Geodict is exporting the stress strain results. You can see that here. That's the result field that you can later look at in the graphical user interface. And now it starts the second load case. And I will not shorten that now to give your computers the opportunity to also perform the simulation so that you also will have the results on your computer. It just might take a few minutes now. So while ElastoDict is running, I will now explain to you what periodicity in structure generation is, as I announced before. In FiberGeo, periodicity means that fibers that end on one side of the volume reappear on the opposite side. You can see that here. That's a structure generated in FiberGeo and the periodicity was activated. And you can hear, for example, this blue fiber, which starts here somewhere in the middle and goes to the bottom, then goes in again at the top. So that is a periodic structure. All the fibers that go out somewhere go in again on the opposite side. You can also see that when you look at the 2D slices, in this case the top view in X direction of this periodic unit cell. When you repeat the unit cell next to the original one, you can see that they smoothly path into each other and form one big structure. So that's the advantage of periodicity. Of course, that also applies to the top view in Y direction and would also apply to the top view in Z direction. So you can see that again, if you repeat the unit cells next to each other, they form one continuous big structure. And of course also in 3 dimensions. So you see here that's now 8 times the unit cell repeated. And you can see that this blue fiber, which leaves the bounding box at the top, goes in again at the bottom. So now that's a periodic fiber structure. And I said to you that we cannot do that with endless fibers. And the reason is that if we had an endless fiber, it would leave the unit cell at one end, go back in at the opposite side, leave it again. So we would have like an endless loop of the endless fiber leaving the unit cell and going in on the other side. And of course that does not work. When you have a structure that has not been generated as a periodic structure, the fibers just end at the domain boundary. You can see it here. This blue fiber ends at this boundary and it does not go in anywhere else. That also means that these non-periodic unit cells do not form a large continuous structure if you put them next to each other. So if you repeat them, as you can see here, they are not one big structure, but they are just 4 structures next to each other without any real connection. So here you can see a model of the 8 non-periodic unit cells put next to each other, and they do not form one large continuous structure. Whether a structure is periodic or not also has an influence on simulation when it comes to choosing boundary conditions. When you choose periodic boundaries, all the information at the edges, for example in this case here the strains, so that's a tensile test on the periodic structure I showed you before, and here you can see the strain distribution. So the strains that are here at the outer voxels at the boundary are also again present at the first voxels here at the bottom. So this structure is treated as if the unit cells were repeated on all sides. And that only works with a periodic structure. When you set up a simulation, you also have the opportunity to choose symmetric boundary conditions. And I will show to you what that means, again on the example of the periodic structure I showed to you before. So to compare it to the previous results, I again repeated the unit cells next to the one unit cell which was considered during simulation. And from these jumps in the strains, you can see that obviously the structure was not repeated to emulate the boundary conditions here during the simulation. So what happened? What happened is that the structure was mirrored. You can see that if you mirror the unit cells, the strain distribution looks quite perfect. The disadvantage of that is GeoDict also needs to keep these mirrored structures in memory somehow, so thereby the runtime increases. But then why do we need symmetric boundary conditions at all? And I can show you that on this example of a periodic simulation on a non-periodic structure. So here the boundaries are again treated as if the structure was repeated on all the sides, and you can see that this leads to high strain peaks at the boundaries, because like here fibers just end or do not go on across the boundary. So that leads to some unrealistic results. That can be overcome by using symmetric boundary conditions, because in symmetric boundary conditions the boundaries are treated as if the structure was mirrored. And maybe as you remember from the previous slides, when you mirror a non-periodic structure, you get a structure that smoothly passes from one unit cell to the next. And you can see here that then you also get an even strain distribution in your simulation. And now we will make a 15 minutes break to give your computers the chance to finish the simulation.